Hello, my name's Joe Greet, and I'll be presenting to you today on the monitoring and evaluation program for Melbourne Water's hydrology works at the Yellingbo Nature Conservation Reserve. I've been working on this project for about 8 years now, since the completion of my studies back in 2012, and I'll be presenting on my work together with work from by my work colleagues Sarah Fisher, Kathy Russell, and Mel Fredrigo. Yellingbo is a very special place. It protects some of our last remaining swamp forests within the Melbourne Water region, in particular the FFG listed Eucalyptus camphora swamp community, of which Yellingbo protects the largest remaining remnant. This habitat provides critical habitat for the last wild population of our bird emblem, the helmeted honeyeater, and provides habitat for the last remaining lowland population of our faunal emblem, the leadbeater's possum. Sadly, these forests are highly degraded in parts and threatened by inappropriate water regimes, with over 30% of swamp forests within the Yellingbo Nature Conservation Reserve dieback affected. And this is likely largely due to inappropriate water regimes, and in particular prolonged inundation of areas that have received sedimentation from channel erosion and catchment processes upstream of the Yellingbo Conservation Reserve. My early work on this project involved a range of field surveys and nursery-based experiments to determine the environmental watering requirements of Eucalyptus camphora and their swamp forests. That suggested that flooding between 3 to 6 months would be ideal, with reduced water levels from November onwards, particularly important for the recruitment and regeneration of these forests. That work, together with a long period of stakeholder engagement from a range of organisations, including Friends of the Helmeted Honeyeater, Parks Victoria, Greening Australia, Zoos Victoria, led to the development of a hydrology works program, which Melbourne Water has led, which has two primary components. The pumping of water from areas experiencing prolonged flooding and dieback, and the removal of levee banks from upstream reaches of the Cockatoo Creek to promote floodplain engagement and regeneration of forests in those areas. To accompany these works, I developed a monitoring program to assess the vegetation response to these works. That program has been running for 6 years now, involving tree condition surveys, using the living MERI method, stand condition surveys, assessed using fisheye photography, monitoring of seed fall and understory and mid-story vegetation condition, and of course water levels. And this monitoring has occurred at sites currently dieback affected or considered too wet, as well as sites considered too dry and intended to be engaged by the levee bank removals, and also includes 2 reference sites, areas with swamp forests of relatively good condition. Water level monitoring over the past 6 years at the reference sites. Those 2 hydrographs here on the left indicate in those areas with good condition swamp forests that flooding typically occurs between 4 and 7 months a year. So largely in agreement with the intended water regime requirements for these sites. In sites that are dieback affected, in the top right, we have one of the wet sites. We observe flooding usually between 8 or more months a year, with very brief or minimal drying periods. Whereas the dry site on the bottom right, there have been very few engagements of that site due to levee banks and the incised nature of the channel in the vicinity of those areas. The pumping trial has been running full steam for the last 2 years and has experienced some difficulties. I should have mentioned that water level monitoring over the last 6 years has indicated a drying trend between 2014 and 2019, with 2019 being a particularly dry summer, in contrast to the relatively wet conditions over the previous 12 months. So in 2019, during the pumping trial, you can see here the level at the inlet site indicated in green. The pump was continually turning on and off due to insufficient inflows to the pump inlet site. And only minimal quantities of water were able to be pumped over the summer period. In contrast, the recent summer has been very wet. And while the pump has been able to operate, it has had limited impact on water levels within the swamp and at nearby sites. Also, over the last 2 years, monitoring has indicated that engagement of the levee banks has been infrequent, and at one of those sites has only in the upstream reaches of those levee breaks, there's only been one engagement event over the previous 2 years. Nonetheless, field surveys over the previous 5 years have indicated there has been improvement in the condition of swamp forests within the wet sites, particularly at one of those wet sites. And photo point monitoring shows this quite clearly, that it's a result of regeneration and increased vigor, particularly of the mid-story woody vegetation at these sites. And this has also been indicated by the fisheye photography monitoring that's occurred within those dieback affected areas. Of course, due to COVID this year, sadly I was unable to get out into the field and conduct the annual field surveys this year. So our efforts have focused on the processing of LIDAR data, which has been captured using drones in flights in 2018 and 2020, and through hydrologic modelling over here on the right. Largely the work of Kathy Russell, who has built a two-flow model to model hydrology across the wetter parts of the reserve. And the analysis of the LIDAR data, I should have mentioned, that has been completed largely by Melissa Fredrigo, has reflected what we've seen in the field, and that's in those dieback affected areas, in these maps represented by the orange areas, and within the vicinity of the pump inlet site, have experienced a general increase in their canopy height over the past 2 years. This is in contrast with the reference areas, in which we've seen variable height increases due to tree fall and tree growth across that period. And this is that same data just represented in box plots. And again, we can see that at the reference sites, there's been minimal changes in canopy height, across the period from 2018 to 2020. However, there's been quite substantial increases, starting from a low base at those dieback affected impact sites. Likewise, if we look at vegetation density, it's a similar story. So vegetation density typically higher at those reference sites and lower at the impact sites, where we've seen a considerable thickening up of the vegetation at those impact sites over the previous 2 years. I mentioned before that we haven't had a whole lot of engagement at those sites where the levee breaks were introduced. And while we've seen some regeneration of Eucalyptus camphora at those sites, that's been relatively minimal due to infrequent engagement. And that's probably largely due to the incised nature of the channel and the increased channel capacity in the vicinity of those levees, reflecting historic channel erosion. So some good work by Kathy Russell explored options to introduce in-stream structures in the vicinity of those levee breaks, and that modelling showed that that would be likely to lead to considerable increase in floodplain engagement in terms of flooding extent and duration, and in providing more appropriate wetting and drying regimes at those sites. So that's something that we're looking to explore next year and in the coming years. And there's way too many people to thank that I've worked with on this project, but here are some of those people. And of course, we acknowledge the Wurundjeri people as the traditional owners of the land on which this research was conducted. Thank you.